Related rates applications. Day one. Now, most of what we're actually doing today is going to be more important for tomorrow. Tonight's problems, like I said, are Delta Academy. You've kind of seen some of the problems in your last night's homework where it's like the two formula one. I really, in the homework, that the problem with the circle with the area and the circumference, and then it asked you for like the radius while giving you like the circumference. Those are, so you have two. I only assigned two sets of problems tonight. One of them just uses one formula, so it's just going to be looking like your normal formula, and it'll be something with an application, or it'll describe the shape that you're using without explicitly, oftentimes explicitly saying a shape, but it could. Um, and then there's another set where it's going to utilize two formulas. So it might utilize like the circumference and the area, or it might use the surface area and the volume. Um, so we might ask you for, might give you the information for here's dVdt, and then they ask you for dsdt. But in order to find dsdt, you first need to find drdt using the rate of change for volume formula. Most of tomorrow's problems are a little bit on the longer side, but basically I'm giving you all of class time to be working on it as well. I'm going to help you set up some of those problems with your help. I'll help set those problems up, and then you can utilize the time of class really to ask any questions, because there won't be much follow-up. I'm just expanding the time we have on this topic right here by an extra day. All right. So when we say applications, we typically mean just real world context. Okay. As such, we have this step 0, which I just call as like an initial step that always helps you. And that's to just make a sketch and label. So you want to draw out what's happening, and also very importantly, you want to identify any constants. If a side length is changing, label diagram with variable and not value at the instant. If a side length is constant, label as value and also into formula being used in relationship. Okay. Now, you could instead decide to go the route of labeling the side lengths with the variable that are constant as well. All right. So if label sides as variables when in fact constant, just note that dt will be 0. So whatever that variable is, that the derivative will be 0. But this typically harder to do. So those are typically harder problems to do. I'll give some time to catch up on there. See if there's any questions.
Sorry, I have a question.
Mm-hmm.
What does it say after when in fact after that on the in the blue?
Constant?
Okay, thank you.
Just note. That should have been said just note. All right. So here's an example. A rectangular pen has a fixed length L of 5 centimeters and a width W that is increasing by 2 centimeters per second. Find the rate at which the area of the pen is changing at the instant the width is 7 centimeters. Okay, so what's my shape?
A rectangle?
It's a rectangle. Perfect. Now, I could just label this as length and width like this, but what do I know about one of the sides?
The width is 5.
No, it is not.
Length is 5.
The length is 5, and it's constant. So I know that L is constant. So this is always 5. Okay? And I know that dw dt is
2.
2. And
Positive 2.
Positive 2. And W is
2.
W is
Would it be 7?
yeah, 7. So dw dt was 7 centimeters per second. And yeah, I like the units in here sometimes. All right, so what is, and I want to know what is the area. So I want this relationship between area, length, and width. So what is my area formula?
A equals length times width.
Good. But since one of the sides is constant,
A equals 5W.
Perfect. Therefore, now we go to rate of change.
What, dA?
Yeah, so, sorry, this question wants dA dt. So dA dt is
5dW dt.
which is 5 times
2.
2, which is
10.
10.
Centimeters squared per second.
Yeah, so area squared centimeters per second. Area increasing by 10 squared centimeters per second. If this is more so for tomorrow's work, I'd like you to write your answer in context. But of course, if it's like delta math or multiple choice, we got that 10. Units are important for the problem. Now, I could have solved this problem with L as L, and then my area would have been a product rule. All right, and then I would have also noted that dl dt is 0. So it turns out in this problem, now I could have done that. In this problem, it gave me the width, and it actually turns out I don't even need to know what the width is, because we never use that in my final answer to find dAdt. And that's because, of course, the length is constant. So sometimes in the problem itself, it might not even give you the width. And you're like, oh, I didn't even need to use it. Questions on that problem? All right, then. Example. A 6-meter ladder is leaning against a wall. The bottom of the ladder is being pulled out from the wall at a rate of 1/2 meter per second. How fast is the top of the ladder falling down when the top of the ladder is 5 meters high? Okay, so this one's all about, it's really all about drawing the diagram, all right? So this type of ladder problem is a very common problem in the AP exam. In fact, the right triangle problems are, I would say, the most significant type of problems. We'll see some, we'll see ones tomorrow. We'll see, yeah, we'll see some more tomorrow. So what type of, well, I just told you, it's a rectangle. And the idea here is that this right here is my ladder. And this ladder is 6 meters. Okay, so this ladder is always 6 meters. Let me label my other variables. Now, if you wanted to label this as Z, you could have done that, where Z is constant 6 meters. I always like to write that down. Always identify your constants. And I got to label my other sides, all right? So I'll call what? Well, I'll call the side on my left what?
A.
You want to call it A? Okay, we'll call it A. And the other side?
B.
B. All right. Now, this question gives me other pieces of information. It tells me what? So we're taking care of this. It's a 6 meter ladder, so that's telling me that that ladder was constant, that that length is constant. What other information is given?
1/2 meters per second.
Okay, so what is that based on my diagram? The bottom of the ladder is being pulled out. So the bottom of the ladder, this is going to the right. And the,
so it'd be dB dt.
Yes, dB dt. So dB dt is 1/2 meter per second. Good. What else do they give me?
The top of the ladder is 5 meters high.
Good. So what does that tell me?
A is 5.
And what is the question asking me for?
How fast is the top of the ladder falling down?
Which is?
So would it be how fast?
Anybody else on this one? How fast is the top of the ladder falling down? So what is it asking me for? First off, it's a rate. So which rate would it be?
Would it be the A1 dA dt?
Correct. So it's asking me for dAdt. All right, so I have A and B. I have information around C. So the best thing I can do is set up the relationship. So it's a right triangle. We're only talking about side lengths here. So the relationship that I'm going to use is what? What is the formula? Yeah.
A squared plus B squared equals Z squared.
Yeah. If you label that as C, it would be the same problem. I always like to label as Z. I typically also label my side lengths as X and Y in these situations when I have actual applications, just because I want to know left and right versus up and down. But we have that, but one of them's constant, so I can write A squared plus B squared equals 6 squared. Now this just makes my problem easier. I like to, when I know one of the label sides is constant, I plug it in. If you left it as Z squared and then took the derivative like your previous homework handout was, like your last night's homework was, or not last night's, Thursday's, you could have done it as well and then just note that dz dt is 0. Okay. What do I get as my derivative? What's the derivative?
For the formula, for the A squared plus, okay. So it'd be 2A times dA dB, dt plus 2b times dB dt equals 0.
Perfect. 0 because the right-hand side is a constant. It doesn't matter that it's a constant squared. A constant squared is still a constant. Now, you can also realize that the 2's would cancel each other out with the 2. So if I divide everything by 2, it still works out. So I get A dA dt plus B dB dt is 0. Technically, I'm just dividing out by a 2. All right. I am looking for dA dt. I know A. I've been given dB dt, but wait a minute. I still need to know what B is, and none of the information in the problem tells me what B is. What do I do?
We can go back to the original equation where it says a squared plus b squared equals 6 squared. And then we plug in a, and then we know what z is. So the fox is solve for b.
Perfect. So 5 squared plus B squared is equal to 6 squared. I need to find B before I find A. Good. So that gives me 25 plus B squared equals 36. So B squared is equal to 11. So B is equal to
square root of 11.
Yeah, and it's application, so there's no plus or minus needed here because it's a length. So B is 11, and now I have that information. All right, what do I do to finish this problem?
Plug in.
Plug in. All right, so when I plug in, I get
Wait, we're plugging it into the a squared plus b squared plus 6 squared, right?
the rate of change. Always we're looking for dAdt. So the goal is, what is dAdt? So we want to plug into that rate of change formula. The only thing that you'll ever utilize for the original formula is if there's a missing side length that you need to first off, you'll use the original formula to find your rate of change formula. And the only times that you'll use the original formula is if you're missing one of the side lengths and you need to utilize it to find it, just like we did right now. So we'll plug in, we get what?
5 dA dt plus 11. Square root 11 times 1/2 equals 0.
Good. So this gives me 5 dA dt equals negative square root of 11 over 2. So dA dt is equal to negative square root of 11 over...
It'll be 10 over 10.
Perfect, over 10. And so top of the ladder is falling. It's negative, so I'm going to say the word falling, which makes sense, right? Always think about it, right? If this length is going out, if B is going out, then A has to be falling down. And so that rate, my numerical answer for dAdt should be negative. But if I'm trying, and if it's a multiple choice, that's all I would give right there. But if it's an open response, I need to have context, and I'll say falling at square root of 11 over 10 meters per second. We never say like it's increasing by negative, and if you say falling at negative, that's like it's like a double negative, which wouldn't make sense. This is more so of an important note. Um, the area, volume, are surface areas are sometimes given as constant, i.e. dA dt is 0. Okay? You can still do the same thing of plugging in, but you need to be careful. All rates are really constant rates. Do not confuse as constant. So there's a difference between a constant rate and a constant. Whenever we say constant rates, so for example, when I said the ladder is being pulled out from the wall I could have said at a constant rate of a half a meter per second. I could have said that one. I could have said it is increasing by a constant rate. I could have said that for this one as well. Constant rate and being constant are two different things. Okay, so do not confuse constant rate and think, oh, that side is constant. All right. If it tells you that like the height is constant, that's okay. That's constant. That's when you can replace. Versus a constant rate, it is increasing at a constant rate. It's still changing. All right, so it's still a variable. I want you to start doing your delta math. I want to spend some time tomorrow to go over like the homework handout and give you some more examples. This material is mostly about trying to do these problems yourself. If you're going to tutoring with we have a lot of different ones. Try to see if you can get any of them on your own at first. Of course, first and foremost, and before you spend extra amount of time just trying to do each individual problem. So I do recommend you spend the time that I'm going to give you right now to start on those problems. The one formula problems should be relatively straightforward. Some of the problems will say, it'll tell you the shape. It'll tell you it's a right circular cylinder. It'll tell you that it's a rectangle. It'll tell you that you have a right triangle in tonight's homework. The one formula problems I think are relatively straightforward. The only things that'll be tricky is, of course, the labeling and understanding if certain parts are constants or not. I still highly recommend that you find the rate of change formula on your own. But in our previous notes from last Thursday, you already have Thursday and Friday, you have all of the rate of change formulas there, so you can double check at it when each of the variables is changing. Sometimes, if you're dealing like we just did, we might be dealing with a right cylindrical cylinder and the radius is constant. It is still up to you. You are not wrong if you decide to still use the product rule for the derivative and for the whatever variable r, if r was constant, for example, you can use dr dt equals 0. You'll get the right answer in the end. Know that you're probably extending the time it takes to do the problem by anywhere between 15 to 30 to 45 seconds, which doesn't sound like a lot, but in the accumulation of the AP exam, if there is a multiple choice, it can add quite a bit of time onto doing the problem. There's nothing more about doing learning and getting related rates by just doing the related rates problems and trying to see as many different types of examples and problems as possible. With that, I'm going to close up shop now. It is 9:42. The rest of the class is asynchronous.